So check this out. If I turn this knob and get a pulse wave come from that Arduino, I can make that motor over there spin. And then adjust it either faster or slower, or crank it up to some pretty crazy speeds. About 5,000 ripums when I checked it from the little tachometer things. Oh man, I love being a dumbass. Like, don't get me wrong, being a smartass is all fine and well, but being a dumbass, it's a lot more fun. Today we're down in the gym and working on some gym equipment, but of course this project is really for the shop. What we have here are the guts out of a few commercial grade treadmills, because a year and a half ago I accidentally bought 5 of these for $5. Now when I say accidentally, I mean that I had intended to buy one of them for the motor from a broken lathe in the shop, over in the next room. But with the way liquidation auctions go, sometimes you mean to buy one and you end up buying 5. So I picked them all up, took all the useful guts out, and the rest went off the scrapyard. And now a year and a half later, here we finally are, hopefully going to put some of the stuff to use. And that's a great thing, because there's a ton of useful stuff in a treadmill. Obviously you've got the motor for one, then you've got the pulleys, the pulley belts. You've also got like timing belts, acme threaded rods, lift motors for the elevation, EMI filters, big resistors, the motor control boards. Those will be particularly useful for this video. Rollers, conveyor belts, switches, plugs, just tons and tons of stuff. And obviously the monitor up top too, where you plug in your speed when you're running on a treadmill, for people who do that. I don't know why. Yeah, I don't know why people. Anyway, treadmills are silly. They're much better used in the shop anyway. So that's what we're going to do. The thing I didn't know when I bought these commercial grade treadmills is that they usually have 3-phase motors inside. Typically a much more heavy-duty industrial motor. Well, I'm in my house, so I don't have 3-phase power, right? That's a problem. Usually what you do is you get a variable frequency drive, a VFD, and that can convert the single-phase input into 3-phase output, and also control the frequency, which then adjusts the speed of your motor. Now, back when I bought these treadmills, I did also pick up one VFD, just to test it out and get some experience with how that works, though I have not really set it up yet. The lathe is still broken. The lathe, in time, I'm going to fix it now. Lathe will be fixed. Anyway, I did get one of them, a very nice Hitachi. They cost about $300 or so. Now the problem is I've got 4 extra motors, in the stack, in those boxes right there. And I'm not going to buy 4 extra Hitachis. $1,200 extra in Hitachi VFDs, it's kind of excessive. Now there are cheaper options too. You've got like your Chinesium grade, Hung Yang, burn your house down VFDs, and they run you about $150. But even still, that's like 4 extra VFDs, and you're going to burn your house down. So I don't want to try that option either. But what occurred to me was, these treadmills all ran in the gym off single-phase plugs. So it stands to reason that somewhere in the treadmill there is in fact a VFD. And if you take a look at this guy over here, the power control board, we've got single-phase input, a big old transformer to set the voltage up, a rectifier, a bunch of capacitors, and then 3 pairs of MOSFETs for switching. That looks to me a hell of a lot like a VFD, right? So these control boards are basically, just special purpose VFDs designed for the treadmill. And I figure as long as I have these, I may as well try to figure out how to use them, right? They're probably a lot more reliable, a lot less likely to burn my house down than the Hung Yang ones, and it saves me from spending, $1,200 on another 4 Hitachis. So I did, work my way through this, already figured it out, got the setup here with the Arduino and the potentiometer, and a little breakout board I use for testing, and this absolutely lovely DSO138 oscilloscope. I learned about these things last month, and they are fantastic. It's the most cheap, janky, lovely little oscilloscope you'll ever lay your eyes upon. The whole package here cost, I think $30 shipped with the power supply and the case assembled. Now, the case you do assemble yourself, and that took like an hour, just peeling off all the plastic and screwing it together. That took a while, but now that it's together, it's, you know, a pretty great single channel oscilloscope just for testing and things, you know, especially when you don't really know what you're doing. The way I have no fucking clue. So I didn't want to go and buy a fancy Rigol or anything like that, because I know the first time I use it, I'm going to fuck it up and end up frying my Rigol. So getting a little DSO138 gave me a very easy, you know, thing I can practice on, and if I happen to fry it, it's 30 bucks. I don't need to worry about it, right? You know, if you see my other videos, just how many Arduinos have died at the hands of this sick and twisted bastard, you know, but it's for the sake of science, right? So, yeah, the solution right now has this little potentiometer, and that puts out or gets read by the Arduino, so it puts out a PWM signal, and then that goes to the power board over there and controls the motor. But this whole process of figuring it out took me a little while, and we're gonna walk through how I did that now. The problem we face is the same company made that VFD and that control panel, and they really want you to use them together as a package in a treadmill and not cannibalize them and part them out piece by piece in your shop. And because the same company made both halves, they can put in all the checks and interlocks they want to ensure these two pieces work together, both software checks and hardware checks and anything they want, and as complicated as they want, and not have to publish any documentation on it because it's all the same company making both halves. So our goal is to work step by step and figure out how this works, what the protocol is, and if we can do away with this control panel. I guess technically you could also just use a control panel, right? Put this up by the lathe, put some aluminum in there, then turn it up to 8 miles an hour. If you're putting steel in there, turn it down to 4 miles an hour, a brisk walk. And if you're putting plastic, crank it up to a 12-mile-per-hour sprint. But I don't want to do that. I'm ridiculous. I'm not that ridiculous. And just by the principle of the thing, I want to use the VFD as a VFD without the panel. And as you know, I've already figured it out, but it's the process that's important. Now, figuring it out, for a basic setup might be pretty straightforward. A lot of treadmills, they got a potentiometer slide for the setting, right, for the speed. And if you look at that and read the ohms in it, you can see like, oh, it's just, a very simple potentiometer. You swapped out for your own, and Bob's your auntie. But here, we just have a panel with buttons, right? It's all digital, and it's all over this ribbon cable. So it is really a black box that we have to crack open and look inside. So the first step to that is simply, looking inside, right? Open it up, take a look, and see what you got. That's how I figured out. This must be a VFD from a nominal 120 to 3-phase. And looking at the board a bit closer, we can see some other important details. We've got, this guy here is labeled speed sensor. So you follow this cable and look at, here's probably a Hall effect sensor by this little fin right here that's counting the RPMs and maybe doing some feedback somewhere. So we'll look out for, where that happens. We've also got, the elevation, the lift motor, when that plugs in right there. That's currently disconnected. We've got the I/O interface. Just look around and see, what other labels do you notice? Like there's let's see, a COM. We've got another COM one. One of these here, it's like labeled, let's see. See one of these labels is like PWM. There's a couple of other labels here on these LEDs that will be important. And once we, take a look and kind of see, we'll power it on. Make sure, the whole thing really works. And then, once again, watch how it behaves. So the first thing, when you power it on, we'll see what other LEDs turned on with it. And we got like some flashing ones there, we got a solid one there. So we know that we're looking for something similar when you're running it without the panel. And we hit start, and once again, keep watching and see what else goes on. And here we see the first weird thing. The elevation is locked at 15, 15 degrees, because we don't have that motor plugged in. So this board here is clearly missing some feedback. And even though the motor's turning at a nice walk of half mile an hour, after a moment, we get an elevation stall because of that is not plugged in. So it's like one thing to watch out for. And I gotta hope, once we do away with the panel, that doing away with this elevation motor as well won't be a problem. Now later I gotta figure out how this motor works, because one thing I like to do is take 4 of these and put each one in a corner of my welding workbench, and then have a lifting bench, because that'd be fucking sick. But anyway, so I'll plug this in and keep on testing. Oh, wow, I got the right direction the first time. Look at that. Okay, so now we power it back on. We hit start. And again, we want to watch for the behavior, of how this thing works. First thing it does is it turns that motor because it thinks it's at 15 degrees. And that is indeed lowering as far as I can feel. That's spinning a nice slow pace. And we see now that the LED right there should focus, labeled PWM, is lit up. So there's probably a PWM signal somewhere, right? We've also got 2 solid LEDs right there beside that flashing one. We used to have the flashing back and forth and another flasher. So there's other things to watch out for, the signals and stuff at work. Now with the board here, you've got the speed setting up and down, right? And one other important feature is I noticed you can plug in a speed directly. So you say 5 and then hit go. It sets the speed, but then it reads out the current speed. Okay, so something with that speed sensor then must also be coming back to the board here. Now, I don't know if there's any extra feedback in that loop. If this is like if this also sends additional controls, but we know that this not only sends a signal for the speed, but we know it gets a signal back. And what is that? Is that the PWM signal that it uses to control it, or is that the PWM that gets the signal back? Don't really know, but it's at least a thing to watch out for as we continue doing more testing. The next step is to take out a look at the board and the different things on it. Now, well, I've already unscrewed this one before and taken a look at the underside here, but let me insert a little image and kind of tell you what I want to talk about. As if you look at the board closely, you can tell what on the back of this PCB is the ground, because just by convention, a square solder pad is used for ground. So let me see if I can take a photo of that I've already taken and insert that in the video right here. Now that's some primetime video editing, right? So we have that taken apart and we're looking at the square solder pad, and we're guessing that's the ground. We can also take a poke at some other parts of the board with just your standard trusty ohmmeter, right? And just do some continuity checks. So we think we know what ground is. We've also got all these screw terminals all over the place. And underneath these, we'll see there's a little solder pad as well. So if we touch the ground and touch that and see continuity, that is further confirmation that we've really found the ground, because a screw terminal is the sort of thing you would ground on your board. And sure enough, I found that, and that was hint number 1, So next thing we need to do is start reading off the signals from this ribbon cable. That's the next thing. That's kind of as far as we can get just by looking at it. Now, doing that is kind of a pain in the ass, because those ribbon cable ends, they plug in and don't give you any easy access to the solder pads, right? And the solder pad for this one is between the plastic and the FR4. So what I did was I whipped together a little breakout board. This guy right here. It's not pretty, but it does do the job. I designed this in KiCad. It's KICAD. It's an open source PCB program. I have talked about that before with the Star Trac controller I built for my CNC plasma cutter. But really useful program. I'm still a total novice at it, but learning some things and taking this really tight compacted thing on the ribbon cable and breaking it out to these nice and spacious pins where you can get your meter and get your little DSO138 oscilloscope. So yeah, and I just looked out and that I have 2 of these ribbon cables, so I can plug in one cable down to there, breakout board, another cable over to there. The next step is to hook up our probes and go signal hunting. So we'll put the black one on the ground you've already picked out, and then go reading pin by pin. And remember, as we do this, the worst case scenario is we let the smoke out on a $30 oscilloscope. Really not a big deal, okay? Like, as cobbled together all this stuff is, at least the parts here they're safe, okay? You've got like this little ribbon cable, but all it carries is some, small amount of DC current for the processor on the control board and some signals, right? We know this does not have mainline AC volts on it because it doesn't have the insulation to be able to carry that, right? This would not be UL listed if this were carrying AC volts here. So this all, it's safe to you. The worst thing at risk is this oscilloscope right here. If you happen to short some things out, possibly. If you hook it up right, even this will be just fine. And maybe if you short something out again too, you can kill the control board or the VFD. But as far as I'm concerned right now, I can't use those things in my shop, so they're already trashed to me, right? So I happen to fry one in the sake of learning to use the others. That's, again, it's not a big deal. It's just learning, it's life. So we'll hook the black one up to the ground pin and the red one up to the one beside it. And slide those little sleeves over to give it at least a big covering so we don't have any shorts. And then hit go and see what's up. Now the motor's turning at a ½ mile an hour, and look at that, already struck gold on the first pin. So can't really get the whole waveform in view right now. If we adjust the time scale though, we can. And it looks like we have a square wave at about 72 hertz or so, between 0 and 5 volts. Now all the readings here, they're not super accurate, because again, DSO138, it's a $30 oscilloscope, but for the sake of visualization, it is, it's better than nothing. It's definitely better than a multimeter, because here you can really see the plot and kind of see what's going on. And maybe if we adjust the speed, we'll see that change. And sure enough, that increased to about 145 hertz. So in ballpark a double, at double the speed. If we go up to 2 miles an hour now, double again. And now we're at 296 hertz. So again, double the speed, double the hertz. Okay, so what I want to know now is we drop this back down to 0.5. And then we jump up to 5, as I showed before. Is this what controls the speed and gives the signal to say go 5 miles an hour? Or is this the feedback that tells it the current speed of the motor, right? Because we saw before when you set to 5, it had a readout that tracked the motor speed. So if I plug in 5 right here, hit OK, and we see that keeps shrinking, getting a faster and faster frequency as the motor accelerates. And here we can even adjust the time scale again and get a better view of it. And now it's at 720 hertz. So I guess, so we started off at ½ mile per hour at 72 hertz. Now we're at 5 miles an hour, 10 times faster, 10 times the hertz. Story checks out. Cool. And we saw that does indeed track the current motor speeds. This is not the control waveform. This is the feedback waveform from the little Hall effect sensor. And again, that checks out because the fins on that metal disc will flash by the Hall effect sensor proportional to the speed, and they'll give you a frequency modulated waveform. So yeah, that all works. And I might use this later on, taking the reading off of this to be able to say, how many RPM is my lathe turning, or what's the square, or what the surface feet per minute is on a belt sander. Right? You can read that out again and make use of it, even though it's not the one that controls it. So on the next pin, and we'll keep on looking. Working across pin by pin, I did find 2 others that seem related to the lift motor. One changed state, we need the button to go up, and the other changed state for going down. I'm not sure exactly if that's a feedback or a control signal, but it's something to keep in mind for later on when I try doing that workbench with the lift motors built in. I've also found a few others where, honestly, I have no fucking clue. I hit the buttons on the control board, don't see the signals, or see like it's a high voltage that I can't read anything out of, or maybe just noise in some of them, things you really don't know, But you kind of stumble through and just see what you can figure out. And eventually, I found this one that seems pretty interesting. So starting the motor up, 2, 1, now at ½ mile an hour, we got this little guy, a little, another square wave, but a pretty low duty cycle. It's varying between like, I don't know, 0.5 and 45 on the duty cycle reading here. Again, not very stable because it's a very thin waveform. So let's change the speed setting and see if maybe that changes suit. And now at 1 mile an hour, reading about a 10% duty cycle. And then at 2 miles an hour, reading about 15. So it's not exactly linear. And then at 4, getting about 27, and keep turning it up a bit more. At 8, we're getting about 50%. So this isn't exactly linear, but it does seem to be the PWM signal that controls the frequency the VFD puts out to control the speed of the motor. So we found the feedback and the control for the VFD, and luckily it's pretty straightforward and pretty simple. Not as simple as a resistor you just slide, potentiometer, but we can still take an Arduino at potentiometer and read that, and then generate that PWM to control the VFD. Now, this one, right, it's not the same as that feedback. The feedback changed the reading in hertz, right, the number of waveforms per second. Whereas this guy, pulse width modulation, it changes the amount of high on every square versus the amount of low on every square. And we also saw that it was a pretty consistent, like 80-something hertz. If I pull it up one more time. 2, 1 again. Ugh. Right here, it's like, 85 hertz or so. And no matter what we set the speed to, that pulse, the pulse width, how many waves per second you get, is still about 85. That doesn't change. It's only the uptime versus downtime that changes. Now, in my testing with the Arduino, I found the VFD doesn't really care what your frequency is, luckily, because the analog write function on Arduino by default operates at around 490 hertz for the Arduino Nano I have here. A few others have different frequencies, but it's in the ballpark of a couple hundred hertz. So I can still use that without having to resort to manually programming out the square wave function. I can just use analog write, and it makes it straightforward, simple. Cool. So on the next step of trying that out. Now I got the Arduino pumping at the PWM that we need for the VFD. It is kind of fast at 490 hertz, but I know from hindsight and testing that will still work. And if you really do want to test at the 85 or so hertz that the control board usually put out, you can always do that by just bit banging it out using digital write and delay. So, digital write high to some pin, and then delay for like 6 milliseconds, and then write low, delay for 6 milliseconds, and repeat. And then that would give you a 50% duty cycle at roughly, 85 hertz, because 12 milliseconds into a second gives you, about 85. Anyway, it's making that signal, and its duty cycle for this one is modulated by the potentiometer. So it reads with analog read off the yellow wire, and then does a digital write off this blue wire to the pin we'd found before, controlled by that display over there. And then the green one ties the grounds together so they have a common reference, and it's powered off its own 5-volt supply right there. So that should work now if we power on all this. The control board here is completely unplugged, and the VFD is currently turned off. If we hit the switch, see what happens. And we get nothing. At least we get some LEDs, but no motion from the motor. So what's the deal? Well, we can tell that the PWM LED, it's upside down, but it's PWM, is lit up, so it's getting the signal. But you can see some of the other LEDs that were lit up before are not now. Like that status one right there, it's not turned on anymore. So apparently this VFD can tell that the control panel there is not plugged in, and we need to find a way to spoof that. One minor hiccup, but we can still get past this. So the next thing you do when you're trying to, bumble your way through what this protocol is you go to your trusty DuPont cables here and start going pin by pin to find out what you need to run the minimum amount of stuff on that board. So we already know what ground is, right? We know the ground is the one right there, or equivalently over here on the breakout board. Zoom in really close, manual zoom. So that corner pin is the ground on the wire itself, and then it breaks out to that pin sticking from the far end there. So you know that one's a ground. So now we want to find the voltage in, right? The high voltage for this. So one thing you can do is just get the thing powered back on again and just read from each set of pins, what's the voltage at each spot. And I know from there, we got a couple pins that sit at 12 volts when the whole thing is idle, and a couple that sit at 5. So there's two different voltages that are commonly used on electronics like this. And, well, basically if you hook up one of these pins, or one of these wires here for the ground, and just test one by one each of the other ones, eventually you'll find one that gets some life out of the board. And that one is your VN. Now it turns out that VN is actually a 5 volt signal in this, though there are still some 12 volt inputs as well. I think those 12 volt inputs are being delivered up there because some of these treadmills have a special add-on with a fan that's up top. And those fans typically run on 12 volts DC. So that's probably what that's all about. And all the logic on the board is probably running at 5 volts. So I found that, let's see. I think the one beside it right here is the voltage input. If I got, let's see. Yep, on the top row, number 4, which then on the pin header is the front row, pin 5. So right next to the blue wire, that is your voltage in for the board. And then tried it again, found that, hey, still doesn't work. You know, the board will not power on if I have that hooked up to the VN and ground, but the VFD can still tell that it's not connected in the right way, right? It's still missing something else to make that little LED light up. So again, you go through testing wire by wire, right? It takes some time. You gotta like switch it off each time to help make sure you don't short anything out, turn it back on, and just kind of gets around till you stumble upon the secret, which is, let's see if I can find a female. Here we go. And actually, I'll shut this off first. Yeah, take my own advice and shut this guy off. Right, that is off already. Okay. And I'll turn this one off too, just to be double safe. And then I found that we need to have another pin drawn high. And that's just this guy right here. That normally, that control panel draws this pin high. So now that we've done this, we'll begin putting up the square wave in just a sec. And we power the VFD on. There we go. Haha. And again, you know, it's just kind of stumbling through it to figure it out. But sure enough, that's the ticket. So we were kind of lucky that the motor control could pretty much be isolated from everything else on the board. And the communication between the display and the VFD was not that advanced. You know, it was more than a basic potentiometer motor controller, but it wasn't like crazy with DRM and encrypted TCP or any of that sort of nonsense. So with some troubleshooting and critical thinking, we were able to figure out at least the important parts. There's more left for later, like with the lift motor there. It's currently detached, and the main motor will run now with that detached and the display out of the loop. But I want to figure out how to run that on its own later on for other projects I have down the pipeline. For the time being though, I'm going to just put some of the files related to all of this up on GitHub. Things like just general notes, the PCB layout for that breakout board, the Arduino code, and that kind of stuff. I'll put a link to that down below, and maybe at some point in the next couple of weeks, I'll have a video on my workflow for making PCBs. Because I have a pretty good system now using KiCad to do the layout, and then a K40 laser to etch the mask, then ferric chloride to etch the copper, drill it out, and solder it up, etc. I got a system, maybe I'll do a video on that. And in the meanwhile, if you want to learn how to use KiCad to do the layouts, there's a very good video series I mentioned before called Getting the Blinky by Contextual Electronics. I'll put a link to that one down below as well, but I'd highly recommend watching that if you want to learn how to use some open source tools to design your own PCBs, and either fab them at home or ship them out to some other third party who can make professional grade PCBs for you that way. Anyway, this is pretty fun, and in fact, I enjoyed this whole task enough. I might even spring for a nicer oscilloscope now. Get myself a real Rigel or something, and still use the DSO138 as the gruntwork oscilloscope out in the front lines, just in case I do happen to fry it. But then have the nice one in the background, for those cases where I need either a higher reading rate or more channels or whatever. But again, we'll see if any other projects come up that require that sort of power. For the meanwhile, I'm going to clean all this shit up now and get out of the gym so I can get my swole on. Peace.